Page 19, page 19, page 19. Let's see, who has a nice voice? Max, you have a nice voice. Can you read example 1 for us, please? Can you read example 1 for us on page 19?
Example. You mean the word?
Yeah.
Jenna borrows money from her parents for a school trip. She repays the loan by making regular repayments. The graph shows how the money is prepaid over time. The data are discrete because payments are made every week.
Okay. A, how much money did Jenna originally borrow? Okay, so how much money did Jenna borrow from her parents? 200, right. So remember what y-intercept stands for? Y-intercept is your initial value. So if you take a look right here, your y-intercept right here is 200. So what's my unit since it's a word problem? Dollars, right. Okay, so $200, your initial value. How much money does she still owe after 3 weeks? So if you take a look at your graph right here, weeks are on the bottom. So when you look at 3 right here, you're gonna draw a dotted line. All right, go to your graph and then go across, and that's gonna tell you your answer. Okay. Tomorrow's assignment, you have to show something like that too. Okay. So, how much money did she still owe after 3 weeks?
140.
140, right? Because if you take a look at, remember, you're not counting the number of boxes, you're looking at the scale. You always go by the scale. So between 120 and 160, it's $140. Okay. How many weeks will it take for her to repay half the money? Alright, so half the money meaning 100. So 100 right here, she's gonna go across, and then down. How many weeks will it take? 5 weeks. Good. And how long until she repays the whole debt? Okay. So basically, when is the amount owed at $0? Yancy? 10 weeks. Good. And then how much money did she actually repay every week? Emmy?
$20.
How did you do that?
You compare the y value
Uh-huh.
to the amount of weeks, and you know how it goes down.
Yeah. Okay.
Or whenever you're writing.
Okay, so she borrowed $200 and it took her 10 weeks to repay everything. So when you divide it out, you'll get $20 per week. This is what Emmy was saying too, because if you take a look at your slope right here, okay, your rate of change, you're going down 20, going down 20, going down 20 every week. Okay. The key to this question right here, so getting those numbers is easy. What do you think a common mistake people do in this question? This seems like a straightforward question, but in the past, people have lost like half a mark here, half a mark there. What do you think is the common mistake? Units, right? So for example, some people might say like $5 here instead of 5 weeks, or they say $20 instead of unit rate, which is 2 units, $20 per week. Okay, so be careful with units. Okay, number 2, example 2. Ivan, can you read the example for us?
Maya jogs on a running track. This graph shows how far she jogs in 10 minutes. Assume Maya continues to jog at the same average speed.
Thank you. Okay, so this is Maya's jog. Predict how long it will take Maya to jog 2,000 meters. So for 2,000 meters, should I be looking at the x axis or the y axis? Y axis, right? Because this is the distance. 2,000 is the distance. But wait a minute, it only goes to 1,200. So what do? Keep going on the scale. Right? So it's every 2 boxes is 200. So this one right here will be 1,400, 1,600, 1,800, and 2,000 right here. Okay, so I go across, but what's the problem right here? Emmy?
The line doesn't go.
Yeah, the line doesn't go far enough. So what should I do? Extend that line. But how do I know my line keeps going this way and not suddenly goes this way or like this or stuff? What's the keyword in there that, yep. Okay, but based on the word problem for him? Yeah, same average speed. So she's going at the same rate, same constant rate. So that tells me I can actually extend my line, right, until she runs out of breath. Right, so then it gets me to this point right here, and so when I come down, okay, again extend my timeline as well. Okay, how many minutes does that look like? 17 minutes. Maybe I'm wrong, but 17 minutes. Looks like it's 17. Okay. Predict how far Maya will drop in 14 minutes. So 14 minutes, I'm looking at this on my x-axis, go up to my line, go across. Okay. And what's my answer for B? For head. Um, say that again.
1,700 meters.
Perfect, 1,700 meters. And good, you gave me the unit as well. Okay. And what assumption do we make here? Okay. The assumption that we made when we continue this graph is she was going at constant speed. Will this line go on forever? Will this line go on forever? Who says yes? This line will go on forever. Who says no? This line will not go on forever. Okay, Yancy, why not?
Because you can't jog forever.
Right, she can't jog forever. Eventually, what do you think that graph will look like? So that's a tricky question. That's a tricky question. So let's say after the 17 minutes, she runs out of breath. Okay, she stops. Do you think my line is gonna go like this then? The rest of my line? Do you think she drop dead? Yeah, if she stops. Will it just like be a dot right there? Margaret, what do you think? Horizontal line. That's right. It's gonna become a horizontal line like that. Why is that? Because one, it's not gonna be just a dot because time keeps going. Right. So time goes on forever. So you'll still have a line. And it won't go like that because the distance she ran doesn't suddenly decrease. And then so it's just gonna be a horizontal line where she's not gaining any distance, not losing any distance, but time still goes on. So that's why, like, you know how the heartbeat chart when you die. It doesn't just stop. It goes beep, and then it's a horizontal line. Same reasoning. All right. If you take a look at example 1 and example 2, what's the difference? What's the difference between these dotted lines here and these dotted lines here? Any difference between these dotted lines and these dotted lines that I drew? Which one is more accurate? Yep, go ahead. The first one. Why is the first one more accurate? Not because it's smaller, but because it's within my data, right? This is the given data. And did I need to make any predictions? No. Whereas this one, I had to extend my graph and make predictions. So this is what's called interpolation and extrapolation. Which one do you think is this one? This one is inter or extra? Inter, right. It says inside. So interpolation. This one, notice I had to extend it, so it's extrapolation. Okay, and interpolation is always more accurate than extrapolation. All right, last example right here. Use this graph to determine the value of x when y equals 3. So when y is 3, right, let me first extend my line. So when y is 3, go over, go over, go over, go down. What is the x value? Betsy? When I extend my line, go across -5, right? X equals -5. And what did I use? Interpolation or extrapolation? Extra, yeah. And then for the last one, when x equals 5, right here, okay, and then go across, okay, y equals, let's see, sender, what number does that look like? Looks like it's between 6, 7. Uh-huh.
6.5.
Oh, I thought you were gonna say 6.7. 6.5. Good. And is this interpolation or extrapolation? Did I have to extend the line on this answer? It was between my two data points, right? My biggest and smallest data point. So it's inside of it. So it's inter. Okay. All right. So today's lesson was just reading off graphs, basically. Nice, short, easy lesson. So your homework, basically rest of this chapter. So page 20 to 22. Oops, sorry. Page 20 to 22. Okay. A lot of these are very short. It's just like one number answers. Whenever you see these ones right here, take it further. These are like the extended questions. You don't have to do it unless you want to challenge yourself. So these ones right here is basically the challenge questions. Okay. And then so remember, so right tonight, these ones.
Mr. Howland, could you call 510? Mr. Howland, call 510, please.
So homework tomorrow. Two things. One, Homework check. Okay, so basically all of chapter 5 from page 6 to 22. And then also the in-class group assignment. In class. Friday. Today's Thursday only. Okay. Okay. All good. No surprises.